Unit 15, Part 16. So we can see now how we got the instance we needed here to do the modus ponens, right? We got GA because after we universally instantiated from 1 and 3, the assumption of the conditional proof, right? We had a modus ponens waiting to happen. And so we just modus ponens our way to, right, conditional, got the antecedent to the consequent GA, which is what we needed, right? Remember, that was on the page first before we did the instantiations. So the UG is legitimate. We now fill it out, UG to 7, right? Don't forget to complete the annotation of your proof, right? UG 7, thus now we have this, so we have modus ponens on 2 and 8. See, right? That's finally now we've got the use of premise 2, which was a conditional, so we were put in mind of modus ponens, modus tollens. In fact, we determined that we needed exactly modus ponens to get what we needed, because we needed that consequent. So, yep, UG, modus ponens 2 and 8. We finally got the antecedent of the conditional. Boom, and that's the end of the conditional proof. And don't forget annotating the proof, because you do lose a point or two if you miss a letter or something. We had a question mark here in the last part. So now it is what? 3 through 9, right? Notice again that with universal, a difference between universal generalization and conditional proof is that UG, you only cite the last line of the subproof. Conditional proof, you cite the whole thing. So we've actually gone through both of the ones, both examples J and N. J was in the pure ones, N, this one we did from the mixed quantifier problems, which are the two proofs which she compares the structure of. I put this up before, but on 292, right, she's comparing the structure. So we went through both of them. So notice this one, this is the one with the conditional proof on the outside, and right, the conditional proof's on the outside, the universal generalization is within it, whereas the other one, J, had the UG, the universal generalization on the outside. It was a pure one, right? So the last step was just a generalization rule. And then we figured out that the instance we need was a conditional, so we set up a conditional proof inside the UG, right? UG inside CP for the one we just did, and CP inside a UG for that one. Okay, so let's move on to theorems. So here I'm going to do this very lovely problem Q from page 293. Notice there's nothing up there. The problem is this one here. Okay. Sorry. So it's a pretty long, ugly, disgusting formula, but if you just do, I'm sorry, you've heard this so many times, but if you just do the one, until I get everybody getting it right, I can't rest. If you just do the one thing that you're supposed to do with theorems, then the big, long ugliness goes away and it just reduces to a problem like any other problem, right? This is a theorem, right? We're now learning how to prove theorems in quantifier logic. Recall from Unit 9 what theorems are. Theorems are formulas which are proven with no premises, right? So they're premise-free. The class of theorems is equivalent to the class of tautologies, right? They're always true in every possible world, can't possibly be false. The proof of a theorem always involves making an assumption, first of all. That's obvious from what I already said. Theorems have no premises, right? So this is the big thing, which you've heard me say 100 times, but for those of you who haven't, if in the exam you're asked to prove a theorem, it says prove the following theorem, and then you're given a formula. For the love of God, do not put the theorem at the top of your proof. Right? You draw a vertical line like you always do because you're asked to prove it, so you have to supply a proof, right? If you put that formula at the top, right, what are you doing? Where are you going? You're acting as if you put the theorem that you're asked to prove at the top and treat it as if you're given it as a premise, there's no reason for doing anything, right? What proof are you doing? You are not given the theorem as a premise. You're given the theorem as something you are tasked with proving, okay? So, the big thing to take home is put the theorem at the bottom of the proof. Put that formula you're asked to prove as a theorem at the bottom of the proof. At the bottom of the proof, okay? That's why I've got this without having written anything else, because this is the first and most important step, and if you do this, everything's fine and dandy, right? Because it reduces to a problem like any other problem. I said all these things pretty much word for word in Unit 9, talking about theorems in sentential logic. It's the same with quantify logic, it's just different formulas, right? But problem reduces as before, right? This is the conclusion you're asked to derive. If you've done the right thing and put the theorem down the bottom, right, you now go into your mantra, remain conclusion driven. You say to yourself, what is the structure of this formula? That will tell me what my assumption will be, right? Theorems, you have to make assumptions to begin, because there are no premises. There are no premises, so you can't do anything with any premises, right? There's nothing to derive from premises. There's nothing there, right? So you have to begin a theorem, a proof for a theorem, with an assumption. So remember what assumptions you could make. You could make an assumption for indirect proof. You could do that here, by the way. You could assume the opposite of all this, but that's going to be pretty ugly. Right? You could double negate that whole thing and then do that. But you can, if the formula is in the form of a conditional, then what you should do is set up the conditional proof. Assume the antecedent, right? Put the consequent down the bottom, and then it's just, you've basically arrived at the point where it's a proof with one premise aiming to get that conclusion. The premise is the antecedent of the theorem, the conclusion is the consequent of the theorem, and then it's if the premise, then if what you've assumed. And that's exactly what we're going to do here, because this is a conditional, right? Analyze the structure of that. It's ugly. It's a horrible, horrible formula, but this is a beautiful problem, right? But the quirk, or the wrinkle, the new thing for quantify logic is this could be a universal statement, right? So it could be the case that the assumption you make is, or the first step you make is a flagging step for universal generalization. Flag A, and then there are such theorems for all x, something, something. You'll see some in the examples. Okay, so I've got a lot of space here, but I'm going to need it all. I'm going to get to work on this theorem, okay? So I'm going to set it up. I'll tell you what I'll say what I'm going to do, pause, write it out, and then come back to the next part. But you notice it's a conditional. So what I'm going to do is I'm going to write big long line all the way to the top. I'm going to put the antecedent at the top. So you have to be able to see this and recognize that that's the antecedent, right? And that's the consequent. So I'm going to put the antecedent at the top and the consequent down the bottom, right? As with any conditional proof, it's absolutely crucial, as I've always stressed, to put the consequent at the bottom, right? We'll have the antecedent at the top, and that's what we're aiming for. And then repeat the mantra. What's the structure of this? Well, this is a universal statement. So there's a good chance that I'm going to get that by universal generalization. And indeed I am. So I'm going to do a subproof within. I haven't written the things at the top yet. I'll jump on my chair while I'm paused. And just like conditional proof, with universal generalization, you know you have the advantage of knowing what you're aiming at, right? The particular instance here is FA or GA. When I get that instance, I know where I'm going, right? You should not do this like this. You should always write the antecedent with the consequent, right? But the second line is just going to be flag A, flagging step, brackets, for universal generalization. And at this point, I'll show it with it all on the board, but At this point, it's a bit tricky to see how I'm going to get that. What I've got at the top is a disjunction, right? My assumption, which I haven't written up yet, but it's the antecedent of this, so it's either everything is F or everything is G, right? It's that disjunction, which is not a universal statement and thus is not a premise of a universal instantiation. You can't universally instantiate from that. It's a disjunction. You can only apply rules that apply to disjunctions on that, right? So you're sort of thinking, oof, I probably somehow want to get the negation of one of these sides, maybe not for all x, fx, and then I could maybe, or the other, right? The negation of one of the disjuncts, I get one of them and I can go to the other one, right? It's very hard how to proceed in this one, given you've got this and you're somehow trying to get this within this subproof. Since I'm stuck, what I'm going to do is set up for an indirect proof. What? But, Dan, this isn't the right form for a conclusion for indirect proof because this is not a negation, and indirect proofs result in negations. No problem, kids. What you do is you double negate this, working backwards, FA or GA, right? Now this is in the form of the negation, and what I'm going to assume for IP is not FA or GA, right? And what am I aiming for? Right now, you remember I always talk about the advantage conditional proof and also universal generalization have, and that you can specify exactly what formula ends. You can specify the specific formula that ends your subproof. Can't see that. Right, as we had here and here. Here, with indirect proof, you don't. When does a subproof end in indirect proof? When you have a contradiction. But you don't know, at this stage, when you're working backwards, exactly what contradiction is going to pop out from your premises and the formulas you've assumed and derived, right? So it's going to be, all you know is you have ended the subproof when you have something of the form, Q and not Q, right? Any formula and its negation, right? But you don't know what that is yet. But we will get there. Just before I end this part, I will note that there is a typo on page 293. When Klenk goes through this, so I'll come back with a lot of this on the page, those lines are wrong. Sorry, this is 293. Right, this line, the line that stops at 3 should really go up to 2, and the line that stops at 4 should go up to should not be there. Right. All right, I'll come back and I'll talk about the rest of this proof.